In today's lecture, we will study about intersection of subspaces. Intersection of subspaces. Suppose W1 and W2 are non-empty subspaces of vector space V over field F. Now question is whether W1 intersection W2 is a subspace or not. So let us first see an example. Suppose W1 is a subset of this type A, B, C, D. This element 0, where A, C, D belongs to R. You can see that W1 is a subspace of V, where V is a set of 2 cross 2 matrices with all the matrix entries are in field R. That is A, B, C, D belongs to R. So W1 is a subset of V and W1 is not empty. Why it is not empty? Because the element 0, 0, 0, 0. Because this element is 0 by the property of the element that belongs to W1, and we take here A, C and D, this element 0. So this belongs to W1. So W1 is a non-empty subset of V. Next we check that whether W1 subset of V1 is a subspace of V or not. For this, let alpha, beta, 2 elements belongs to field R and U, V, 2 elements belongs to W1. So U is of type A1, 0, C1, D1 and V is of type A2, 0, C2 and B2. So this type of element U and V belongs to W1. Now let us check whether alpha U plus beta V belongs to W1 or not. So alpha U plus beta V is type alpha belongs to alpha multiplied by this matrix U C1 D1 plus beta A2 0 C2 B2. So when alpha is multiplied to the matrix, it means alpha is multiplied to the each element of the matrix. Alpha C1, alpha D1 plus beta alpha 2 0, beta C2, beta B2. And this is equal to component wise addition. Alpha A1 plus beta alpha 2 0, alpha C1, beta C2 and this is alpha D1 plus beta B2. Obviously there is no comma here. So you can see this elements belongs to R. This elements belongs to R, and this elements belongs to R. So this is of type A3 is 0, C3 and B3. So this is of type A3, 0, C3 and D3. So it belongs to W1. So W1 is a subspace of V. Similarly, if we take another subset W2 of V having element like that, AB00, that is two bottom elements of that bottom row is 0, where AB belongs to R. Obviously 0 0 0, this element 0 matrix belongs to W2, so W2 is not empty, and W2 belongs to W2 is a subset of V. So in the similar pattern as we have solved for W1, you may solve that ki whether an element ki for alpha beta belongs to field R and U and V any two elements belongs to W2 implies alpha U plus beta V belongs to W2. If this happened, then W2 is a subspace of V. Now let us see what is a meaning of saying W1 intersection W2. That is, W1 has an element of type A, 0, C and D, and this element of W2 is of type AB 0 0, such that here we write A1 B1 because these two elements may be A1 B1 is different from this A. So we may write here A1 B1, where A, C, D, A, B, A1 B1 belongs to R. So what this actually means? It means that W1 intersection W2 contain elements which belongs to both W1 and W2. So you can see that in W1, second entry in the first row is 0. So it should be 0. And in W2, the bottom two entries are 0. So they remain 0. And the non-zero entry belongs to the first element in W2 and the first element in W1. So it may be, suppose we write X here. So it means ki the three entries 0 0, these three entries, this 0, this 0, 0, these three entries are 0 and this first entry is non-zero. If we take these type of elements, then this type of element belongs to both in W1 and W2. For example, if we take 1 0 0 0, then this belongs to W1, as in case of W1 this is A equal to 0, this element is 0, and B equal to 0, and C equal to 0, and for here D equal to 0. And in case of W2, this element A equal to 1 here, B1 is 0, A1 is 1 here, B1 is 0, and the bottom two rows of type 0. So this element belongs to W2 because this element is of type W2, and this with these values of A, C and D, this elements belongs to W1. So the elements of type W1 intersection W2 are of this type. X0, 0, it means the second entry and the bottom entries, both the bottom entries are 0. So let us check whether W1 intersection W2 is a subspace or not. Then again, for alpha, beta, any two elements belongs to R, and U and V belongs to W1 intersection W2. Then you may see WU is of type X1, 0, 0, where X1 belongs to R and V is element which is of another element of W1 intersection W2, so X2, 0, 0, where X2 belongs to R. So what is alpha U plus beta V? This becomes alpha X1, 0, 0 plus beta X2, 0, 0. So when these two matrices are added, we obtain alpha X1, beta X2, 0, 0, 0. Since these three entries are 0 and this entry is non-zero, it may be 0, but because alpha X1 plus beta X2 belongs to 0, and this element looks like the element that belongs to W1 intersection W2, so this belongs to W1 intersection W2. So we clearly see here W1 intersection W2 is a subspace of we may clearly see that W1 intersection W2 is a subspace of VF. Now we prove the following theorem. The intersection of two subspaces of a vector space is also a subspace of vector space. Proof: let W1 and W2 are two subspaces of a vector space V over field F. So what we need to prove? To prove that W1 intersection W2 is a subspace of V. For this, let us take two element alpha beta belongs to field, they are members of field, and two elements U and V belongs to W1 intersection W2. As you know that what is our aim? Our aim is to show that alpha U plus beta V belongs to W1 intersection W2. This is our aim. So since U and V belongs to W1 intersection W2, this implies UV belongs to W1 and UV belongs to W2. Now alpha beta belongs to field, UV belongs to W1 and W1 is a subspace of V, so that alpha U plus beta V belongs to W1. Similarly, alpha beta belongs to field, U and V are the members of W2 and W2 is a subspace of V, so that alpha U plus beta V belongs to W2, because this element belongs to both set W1 and W2. So this implies, we can say if this is 1 and this is 2, so from 1 and 2 we have alpha plus beta V belongs to W1 intersection W2. So thus W1 intersection W2 is a subspace of V. One important thing that we have not proved yet, that is the identity elements. Since 0 belongs to W1, as W1 is a subspace of V and 0 belongs to W2. This implies 0 belongs to W1 intersection W2, because the identity element belongs to W1 intersection W2 and alpha for any two elements alpha beta belongs to field and U and V belongs to W1 intersection W2. Alpha U plus beta V belongs to W1 intersection W2. So W1 intersection W2 is a subspace of V. So this is the first theorem. Next theorem is, before starting the next theorem, first we understand what is the meaning of saying intersection WK and K belongs to set of index numbers, or we say A is an index set and K is any indices that belongs to A. Suppose we have subspaces W1, W2, W3 and Wn and many more. So we thought like that कि these 1, 2, 3 and n are the members of A. Suppose A is a set 1, 2, 3, n and this. Whatever be these indices. So A is a set of indices. So instead of writing 1, 2, 3 and n, we represent this set as WK and K belongs to set of indices, that is the set A. So if we want to check whether W1 intersection W2 intersection W3, we do not know how many subspaces W1, W2 we have. So the intersection of all these subspaces we may represent as intersection of Wk, where K belongs to set of indices A. So this is the set that represent the intersection of number of subspaces. So our next theorem is, we may say this theorem is the generalization of the theorem that we have proved earlier. The intersection of any number of subspaces of a vector space V F is a subspace of VF. So proof, let W1, W2 be any number of subspaces of a vector space VF. We need to show that, we need to prove that intersection Wk such that K belongs to A, where A is an index set is this set is a subspace of VF, subspace of VF. Let any two element U and V belongs to intersection of Wk, where K belongs to set of indices. So this implies U and V belongs to Wk for each K belongs to this. That means for every K, that means U and V belongs to W1, U and V belongs to W2 and so on. So this we have written in a single line, UV belongs to Wk for each K belongs to set of indices. Now for alpha beta belongs to field F and U and V is to Wk, implies alpha U plus beta V belongs to Wk for each K belongs to A. Here also for each K belongs to set of indices. So UV belongs to Wk for each K belongs to a set of indices, implies alpha U plus beta V belongs to Wk for each K belongs to set of indices. Since this element belongs to each Wk, so this implies alpha u plus beta v belongs to intersection of all wk's and k belongs to set of indices. So it means कि if alpha beta belongs to field F and u and v belongs to intersection of wk, k belongs to set of indices, implies alpha u plus beta v belongs to intersection of wk, k belongs to set of indices. So one conditions we have already fulfilled by the wk's. Now next, since 0 belongs to wk for each k belongs to set of indices. So 0 is the element of intersection. Thus these two conditions, this and this, are fulfilled by the intersection of the subspaces. So intersection wk is a subspace of vector space V over field F. Hence, intersection of wk's are subspaces of Vf. So that now we have learned today two theorems. One, ki if W1 and W2 are subspaces of, first one is if W1 and W2 are subspaces of Vf, then this implies W1 intersection W2 is also a subspace of Vf. Next one, if we have number of subspaces of Vf, then this implies their intersection is a subspace of Vf. So actually the second theorem is a generalization of this. Generalization means कि here we say this theorem, the second theorem, for particularly for only for two spaces W1 and W2, and this is a generalization because we in theorem 2 we may take any number of subspaces. So let us stop here.